Hello and welcome to the Engineering Dynamics Course Companion Class 8. We're dealing with kinetics of particles, and today it's the work energy method and conservation of energy. And this is part 1 of dealing with energy. We've previously dealt with Newton's second law in classes 6 and 7. So let's get started. By the way, anytime you want, you can click on the links below in the description, and you can skip ahead to the examples. So we start with the bottom line up front. In work energy, the main equation, this is the big equation, and today's we're using blue for our pen. That's a good educational color. The idea for the work energy, this is the thing that we'll write down first when we deal with using a work energy method, is the kinetic energy at state 1 plus the potential energy at state 1, and adding any external work that happens between state 1 and state 2 is going to equal the kinetic energy at state 2 plus the potential energy at state 2. Right. So we'll look at that again and again, but the idea, and this shows up in thermodynamics, the same type of equation. There could be other types of we could have heat types of thermodynamical energy being placed in here, but it's the it's the energy accounting equation. I think some books will refer to this as. We'll also see a similar type of equation will show up in fluid mechanics. In fact, if you recall, well, maybe you'll recall when you take fluid mechanics, as you need to take dynamics first, that you'll have the classic Bernoulli equation is a work energy type of equation. So we define work as the integral of the force applied dotted against the distance that something moves, right? And we'll look at that in a little bit more detail. Kinetic energy for a particle is 1/2 mv squared. You might even remember, it might even sound familiar to you. So kinetic energy is 1/2 the mass times the velocity squared. Gravitational potential energy is going to be mass times gravity times the position. Right, and so a lot of times a potential energy change will be in its difference. The delta potential energy is mass times gravity times delta y, or just weight times delta y. And spring potential energy is 1/2 times the spring rate, or the spring constant K, times the displacement of the spring, and that is not the displacement that it's moved, but the amount of stretch that it has from its unstretched, or the amount of compression as well from its uncompressed state. That squared. And then conservation of energy takes place when there is no external work taking place in here. So one of the very important things to see in the work energy is that we're dealing with scalars, right? That once that we're not dealing with vectors anymore. You'll see that we have a vector here for the force and a vector here for the distance, but there's a dot product right in there, also known as a scalar product. So we're dealing with scalars, and that's a real advantage. It can be a little bit of a disadvantage, but most of the time it's an advantage for working through relatively simple problems to try to remove the complication of vectors. Okay, so the work energy equation, as we've just said in the bottom line up front, is made up of kinetic energy, potential energy, right here. So we have, and those together are the initial energy, right? The energy at a particular state. And a lot of times we could pick different states. So we might not just be state 1 and state 2, but we have state 1, 2, 3, 4. We can move between these. It's often convenient to look through a potential state. So you can see that initially, the kinetic energy is 0 of Wormy as he's attached up into the tree, right? The external work happens to him, so maybe someone pushes down onto there. That would be an external work. You could also consider, we have to be careful here, I have lumped in, some books will say that the external work, that potential energy is a particular kind of external work. But we're going to go ahead and just introduce potential energy as its own thing here. But anyway, something outside happens. Some outside thing takes place. And then in the second state, where we have now we have kinetic energy at the second state and potential energy at the second state, and this is the final energy. So remember just to think about these: initial energy, outside work happens to the thing, and then we have final energy, right? And say, woo, so this is state 2. Now, we don't treat gravity as that external force, although it is an external work. We make it a particular kind of work, and that is the potential energy, right? So we have potential energy taking place. So we define work, as I mentioned before, as being the force times the distance. And it should be thinking force through a distance. And that's what that dot product means, right? Is that the force needs to line up with the distance that it has traveled, right? And that's going to be taking a dot product of the thing, right? And you'll recall how that looks when you do a dot product, right? So a lot of times, though, it's pretty, instead of doing the dot product onto the thing, we could just take and look and see the force that's aligned with the direction of the travel, right? We could just kind of take a look in relatively simple problems, right? If we're not dealing with more theoretical vector type of applications. But just keep in mind right here. So you see that Newt Dog is pushing this wheelbarrow up the hill, right? And he might be lifting, right? So there might be like he's lifting and pushing. But that lifting, as long as that lifting is a constant force that he's trying to lift up, that doesn't count. Only the motion that's in line with the thing, it counts as work. Here you go. So like the weight, right? He's lifting up and he's pushing onto these dumbbells. Of course, you need to isolate this thing if you're into a free body diagram. But we're just looking from state 1 to state 2, right? Kinetic energy, interestingly enough, and this is one of the things that we pointed out in Newton's second law in class 6. In class 6, we made sure that we were clear that when we're looking at something, okay, so I should be a little careful here. So this is one way of approaching it. I was alluding to that Newton's second law could also be the mass times velocity, the time rate change of velocity, right? But anyway, here I've went ahead and I used the tangential direction for the thing. We could see, and this will give us the same thing here. If we take and we take this acceleration and we turn it to velocity times dv ds right here in the tangential direction here, what we can find is that we have mass times velocity times dv ds. We could bring that ds over onto the other side, right? So that's the delta amount of distance that is moved. We integrate both of them, and what we could find is we have 1/2 mv squared state 2, 1/2 minus 1/2 mv squared state 1. So this over here on the left is work. This over here on the right is a change in kinetic energy. So we can see that there's a relationship, and we define kinetic energy state 1, state 2, and kinetic energy state 1. So here's like a way to think of some of the connective tissue between them. We also have gravitational potential energy, right? So this is the weight, the mass times gravity is the force that's acting onto the thing, and it changes from one state to another, right? And so we define that work that's taking place between those delta, and then so we define a particular energy at each of those states, right? Spring potential energy. Now we know that a spring rate is going to be force and deflection, right? With increased deflection, we have increased force, and it's if it's a linear spring, it's by a straight line, and it's really the slope of this curve right here, right? So as you move up this curve, here's the unstretched position. If you put a force F1 onto it, it goes to a displacement, a del 1. Here. If you put some more force on it, F2 right here, it stretches to the del 2 right here, right? So, and we could say that these dels are going to be the length, the initial length of the thing. I think maybe I should have written that out in the other direction. Yeah, I think so. I should have taken L1 minus LO. But anyway, if we integrate those things, we notice that the K is in there, the del is in there twice, right? So this is the distance that the thing is moved but we could also substitute that back in there, so that ends up being K del squared as part of this. And that represents right here. So if we went from state 1 to state 2, that's actually the area underneath this curve. And this is actually, you could think of this as strain energy when it comes to what's happening inside the spring. It's a stored energy, therefore it's a potential energy. But it's also what's special about the potential energy in terms of a form of work is that the path that you take between the initial point and the final point doesn't matter. It is independent. It's path independent. So that's why it is a type of work, but it's its own special type of work, right? And then now we have the conservation of energy that says the energy in the beginning equals the energy at the end. That means there's no exterior work that's taking place onto the thing. Right, so a pendulum is a good example, or even an apple falling. Right, we had potential energy turned into kinetic energy, and one important part of the potential energy when it comes to the gravitational is we need to create a datum. Right, that's going to be some spot where we say that's where zero potential energy is going to be. Right, so the idea here is that we're trade off. When there's a conservation of energy, there's no external work going on here. So we start out with potential energy and no motion. Then we have kinetic energy when it gets to state 2, all right, and no potential because it hits the datum. And then if there's no external work, it will rise up to the original location right here. And you'll notice, by the way, here's another instance where mass could potentially cancel out in here if we were trying to find something. So it's kind of interesting that takes place. So I went through this. I don't think we necessarily need to go through all of these steps, but I will mention sometimes you want to, if you're working on a problem, you want to make sure you do an FBD and IBD. To try to check and see what the normal forces are, because sometimes there's going to be a friction force involved. If there's a dependent motion part of the problem, like maybe there's some pulleys involved, you want to do all those types of things. And then you want to maybe redraw the problem, but draw it in different states onto the thing. I prefer to draw it in dash line in the secondary state, but you should label what those states are. And be careful not to make too cluttered. And then you'll want to label the states. So there might be multiple states. There might be an important thing that takes place at a certain location. And we'll see some problems maybe take a look at there. So an example might be if a block were to be to fall and land, and then a rope becomes slack and like it's connected to another block right there. We as soon as the rope becomes slack, the tension goes away that's on the other block. All right. So I have an example where I show where that happens. And make sure we establish a datum. And usually there's a good strategy to pick a spot where either the beginning is 0 or the end is 0 or something along those lines. I try to avoid having negative potential energy when it comes to the gravity. And then you want to write out that work and energy equation, write it all the way out, and then start thinking about each of the terms that are taking place. And then you want to enter the knowns and identify the unknown parameters. And you might need to go from step 2 to link the unknowns. When sometimes there'll be extra equations that you're going to need, so that might be what happens in step 2, right? And if necessary, you might want to need to repeat steps 6 and 9 for additional states, right, that happen. Okay, so here is a problem that's the same problem as we did in class 6, where we have this block and it's going to move up the slope. The block weighs 25 pounds. It starts from rest and it's positioned with a 25-degree angle at theta 1. And the incline has a static coefficient of friction of 0.25 and a kinetic coefficient of 0.2. And the force that is applied at theta 2 equals 15 degrees from horizontal. And we want to determine the distance up the slope that it will travel when it reaches 3 feet per second, right? So we'll walk through this problem through the steps as labeled up above, where step 1, we want to make an FBD and an IBD, and then figure out what the normal force is going to be. right? So we went through this before, and we get that same 54.8 pounds. So look back at class 6 where we talked about this a little bit more. And we also said in class 6 that we had to decide whether it was going to move or not. We're going to go ahead and skip that because we already decided this force was sufficient enough to push it up the slope, to overcome that static friction. Right? So we find what the friction is going to be using the kinetic friction, that 0.2 coefficient of friction. And now there's no dependent motion, so we can skip, right? We might have been a pulley problem, but this is not a pulley problem. We redraw the problem like I did right here. And don't be lazy. Go ahead and draw this out right here because you're trying to think through what's actually taking place. This is your problem-solving strategy. So if you skip stuff and you're not doing, you're struggling with it because I didn't want to bother to draw the thing out. Use more paper, make more drawings. It helps you think your way through a problem. It'll help you become a problem solver to draw more things. So you calculate the stage's vertical distance from the datum, right? So we establish that it's initial because it's moving upwards. We'll start the original position is going to be y1 will be 0. And so y2, we want to figure out the vertical distance that is moved. And then we write out the work energy equation. And then we start populating that work energy equation. We know that it starts at 0, so the initial kinetic energy is 0. It starts at the datum, the initial potential energy is 0. It moves upwards along delta S, right? But the thing we want to notice is that it's only the force in this direction. That's the only force that we care about. So we need to find out what that horizontal force is. That this is P right here, but some of that force is only causing the thing to be pushed down harder against the surface, right? So that's the work that's being added. But now we have a negative right here. So why is that a negative? Well, we could think of it in two different reasons. One is the friction robs energy from the system, right? We could also say that the friction force is in the opposite direction. Remember that we were taking the integral of the dot product of the force and the displacement, right? Or the motion. And they were dotted against each other. Well, if something is in the opposite direction, two forces are in the opposite direction, and you dot them, it's a negative number because that's the cosine of theta. If theta is the angle between the two forces, right? Well, the angle is 180 degrees, and the cosine of 180 degrees is negative, right? So you can think of it either way, but that friction force robs energy away, so that's why it's negative. So, and then we're marching through that work energy formula, and we get the kinetic energy at state 2, 1/2 mv squared, and the V is the V2. And the potential energy is now the new location of the thing, remember? And we found up above, I think it was in step 5, that we found what that Y is going to be, the Y2. So now we enter in the knowns into the equation right here. And a really good, this is, I think, a very important thing that gives us some insight into what's happening in the problem, is to figure out those the magnitudes of each of these parts. Don't just plug it into your calculator and hit the end onto the thing, because we can figure out if something goes wrong, you can go backwards and try to backtrack and try to figure out, like if you get like a negative, if you have to, sometimes like you might be looking for the velocity and you have it squared, so you have to take the square root, but it's a square root of a negative number and you can't figure, well, that doesn't work. Well, you made a mistake somewhere. So you want to go back, and by writing down these in-between values, you can kind of try to see where the culprit might be when you make a mistake. So there's also, as I tried to say, there's some physical significance. You can see what contribution each of the different parts of this equation is happening, and what is influencing the result. So you can see here that we have a delta S in 3 different spots. One due to this the force P that's being applied. One of them is due to the friction, and one of them is due to the change in potential energy. So we solve for this. It's the only unknown, and we get 2.5 inches. That's the same thing that we got from example 6.1. and steps 9 and 10 aren't necessarily in this problem, but we check back and we see. We'll also use this in impulse and momentum just to demonstrate how it works. Okay, so for more examples, please check out books right here. The links are down below in the Morgan and Claypool website. And you could buy, there's a 2-volume set. You could buy them individually, or you could buy them as a 2-volume set. And please also subscribe to the channel. I'll be adding many more videos. So thank you very much. Wormy and I appreciate you being a constant viewer. Right? Yeah.